Hi, this is the third lecture in the module on condition assessment of concrete structures. In this, in the first two lectures we covered service and exposure conditions, visual inspection and testing of concrete at site, and in the second lecture we covered testing of concrete in laboratory on both the specimens prepared in lab and obtained from the field. And today in this lecture we will cover testing of rebars in field and laboratory. We will look at both mechanical properties and corrosion properties. Now, before getting into the various tests, we will look at what is the need for non-destructive corrosion test and mechanical test. And here in this picture, on the left side, first picture, it says a concrete wall with no visible corrosion or no stains of corrosion is visible. The same wall, after removal of the concrete cover, it was found that significant corrosion was found on all these rebars which are visible now, or exposed rebars. Significant corrosion was found. And the third photograph is showing a close up view which very clearly shows significant, almost nothing is left in that particular rebar. So, the point here is that even though you may not see corrosion stains on the concrete surface, there could be significant amount of corrosion. Significant corrosion could be happening inside the concrete structure, or steel might be corroding in a hidden manner. So, we need to have techniques which can be utilized to detect corrosion as early as possible, and non-destructive techniques are very much useful in such cases. And this is I already discussed this in one of the previous lecture on pre-stress concrete, but I just want to recap on that. The first picture is this one. It shows how the cracking can happen in case of conventionally reinforced concrete with a with a solid rebar. And the second, this one is on how the system is in case of a pre-stressing strand. So, what happens in the case of pre-stressing strand is the corrosion products, initial corrosion products will occupy these triangular space available between the 7 wires, and until that space is filled up with corrosion, you will not see or there will not be significant expansive stress on the concrete or on the surrounding concrete, which is not the case of solid reinforcement. So, what it means is there could be a significant delay in the generation of expansive stresses and the corresponding cracking and manifestation of corrosion product at the concrete surface in case of a pre-stress concrete system. Now, this is again the same slide which was discussed in one of the previous slides. So, basically showing one important aspect that until about 6% of cross sectional loss, there may not be significant visible signs on the concrete surface in case of pre-stress concrete. So, it is very important for pre-stress concrete to adopt employ non-destructive testing and detect the corrosion as early as possible, because in case of pre-stress concrete, once the corrosion starts, it is very dangerous. So, we have to take a preventive maintenance approach in case of all the concrete structures. So, we must be able to detect corrosion as early as possible, or even before if possible, to be able to judge when it will start corroding, so that we can take preventive measures. Now, let us say you left the structure without any monitoring, and eventually you will reach a stage like this, severe corrosion, and then you will have to assess the residual capacity of the structure. And typical practice is that if there is about 10% metal loss, then we say okay, the rebars should be replaced, or it should be taken up and replaced with a new rebar, or some kind of major repair or retrofitting has to be done. And the point here is the challenge which the engineers or inspectors face is, yes, on the documents they will say 10% area loss of the rebar, but how do we really estimate or measure this 10% reduction? It is very difficult, by just by looking you can only say there is significant corrosion, but if somebody is telling exact amount of percent mass loss, it is quite difficult to the correctness of that assessment is not well established. I am going to show you something on how what is the effect of such cross sectional such change in cross section loss on the stress strain measurements which you take. I am not saying stress strain behavior, but I am telling if you take a corroded bar and do a tensile strength test and get a stress strain behavior, how correct that could be. That is what the idea here is, and I am trying to show you that there could be significant changes in the from the true behavior. Let us say this bar here, as you see on the bar on the left side, there is significant change in the cross section along the length, and as you see on the picture on the right side, you can see over here there is a significant loss, over here there is a significant loss. So definitely when you put stress on this bar, axial stress, axial load on this bar, the stress experienced by the region inside these red markings I gave is much more than the stress experienced by the region outside those red marking. So definitely the different points experience different stress, and that in such case, see, if you put, let us say in this bar, if you are actually testing, if you put an extensometer like I showed here, let us say this is E1, I am going to call first extensometer, and then another extensometer you put here E2, and then one more if I put E3. Okay, so there are 3 extensometer if I attach to a particular rebar and then do a tension test, I will get very different stress strain the stress strain graph which I procure based on these 3 extensometers will be very different. So which one is correct, which one is, so basically you are taking an average of the strain within that region, so that leads to a lot of problems. So which does not really tell you what is actually happening at various points on the corroded rebar system. And like I mentioned earlier, there is also a difficulty in assessing what is the cross section loss. So I am just showing you multiple methods which we ourselves did it in our lab, and we found that most of these methods do not really give a reasonably accurate or sufficiently accurate cross sectional area loss. So first one you can see on the picture on the left side, you have vernier caliper, you can measure, but imagine it will measure only the diameter, not really give you the cross section, or how the cross section look like, it cannot really give. So you cannot even assume that wherever you are measuring that diameter, you cannot assume a circular shape. I will show you that in the next slide, how the shape at various locations of this particular bar was. I will show you in the next slide. And then the second method, liquid displacement method. Even here what we tried was we put a graduated cylinder in which you immerse, you first place solution in that and then immerse a rebar and then try to see how much dislocation, how much displacement is, how much water is displaced, and even that did not give you much accurate result. Even we tried with kerosene, even that did not help much. Then we also tried with wax molding, making a mold out of wax and then try to get some idea on how the cross section varies along the length of a rebar. But these are all very difficult to do test, and it does not really give sufficient accuracy in the readings, so it does not really help at the end in estimating how much cross section loss. Then for a research purpose, we did this study on a particular bar. You can see there are 13 specimens of corroded rebars were collected, and then cross sections or most severely corroded cross sections were selected, as you see on these white dashed lines. You can see, and the top of this sketch or the drawing, you can see that how the it is never circular in nature, all these are of different shape. So imagine now if we were using a vernier caliper and trying to measure the diameter and then estimating or assuming it to be a circle, how wrong that diameter could be. So bottom line is it is very difficult to measure cross sectional area loss, especially over a length of the rebar, and we need to come up with, maybe in future there may be a better ways of estimating that, but at this moment this rapid prototyping technique seems to be a useful thing. But the challenge here is we cannot do this at site. We have to extract the specimen, bring it to the lab, and then very tedious procedure in getting properties, in getting the cross sectional variation along the length. Now once when you talk about a corroded rebar, like I mentioned earlier, the stress strain behavior can, because during a test the different points on the rebar might experience different stress depending on the cross section at that particular level. And so DIC or digital image correlation technique is a useful technique which can be utilized to see how much or what is the variation in the stress at various points on the rebar at a particular loading conditions. So you can see here digital image correlation. Here you have undeformed region and then the deformed region. So basically the idea is, in the undeformed region or before the testing starts, you apply black and white speckle surface. Basically you have a black surface and on top you spray white paint, white speckles, and then you can look at get the pixel. So take an image and pixelate it, and then or take an image and then read the pixel by pixel, and then after or during the stress strain test, during the tensile strength test, you can see how each pixel is moving, and then based on that we determine what is the local stress strain behavior. We can find that. So this is a setup to capture these images. So basically during the test we capture several images using this camera, high resolution camera setup, and then post testing we can analyze the data and then see how the stress strain behavior is at different points on the bar. This you can see one example video, very short video I am going to show you here, and you should look for the change in the color. So the more the reddish, it means higher the stress, and then more if it is more bluish in color, then that region is experiencing less stress. So in this video you will see that the stress behavior, the stress at different points are different, and I will take you through until the failure of this specimen. So you can see here in the beginning, and also along the horizontal section itself there is a lot of variation. Now you can see in some region, especially here, there is a stress concentration, and you will see that region is going to, the stress at that region is going to build up and eventually it is going to fail. So that is a critical cross section which we have to worry about, which is very difficult to now the specimen has broken. So, how do we get that in the very beginning? It is very difficult. So, rapid prototyping is a good way of if we want to really understand what is happening in the steel. Now, here also you can see all these different specimen. Look at the solid curve which shows the engineering stress. You can see same rebar, but different points they are actually breaking at different load conditions, and also at the elongation experience is also different. So, very clear that the stress strain behavior is different for different points at the different points on the rebar, corroded bars. Now, ASTM C876 test is something which is widely used for assessing the probability of corrosion in concrete reinforced concrete systems, and the method basically depends relies on the principle that if there is a more negative potential, that indicates more or higher probability of corrosion. So, you can see here this is ASTM standard, but it says that if the potential is less than 350 millivolt or 0.35 volt, then the probability of corrosion is about 90%. If the potential is more than minus 250 millivolt, then there is no chance of corrosion, basically 90% chance of no corrosion or 10% chance of corrosion, and if it is something in between, then you have to really make your engineering judgment. So, let us look at this sketch at the bottom how it works. You can see the rebars, and then with the rebar is directly connected to the positive terminal of the multimeter. You can see here the positive terminal of the multimeter, and the other terminal is connected to the reference electrode, which is this reference electrode. What is a reference electrode? It is an electrode of which the potential is always fixed, it does not change. So, wherever you take this particular electrode, the electrode has a particular potential. Okay, so, that is the whole idea. So, it does not matter which electrode you use, all you have to do is you have to make the corresponding adjustment. So, you have to see what electrode. Mostly people use this copper sulphate electrode, and these numbers are actually based on that. These numbers are actually based on copper sulphate electrodes. Okay. Now, I will show you this picture here. Here this man is actually taking measurements using a wheel electrode. Where is a wheel electrode useful? When you have a large surface area to cover, then such electrodes are very useful, because you do not have to go for point by point, but you can move faster along the surface. So, this is a simpler schematic showing how the this particular potential measurement works. You can see the one main thing in this, you have to really get a real connection, actual electrical connection to the rebar. So, how we do? We drill a hole at some point on the reinforced concrete structure and connect to the rebar, and then the other terminal is connected to the reference electrode, and a good contact at the concrete surface is also required, and then you have concrete here. So, the moisture condition of the cover concrete plays a significant role in the measurements which you get. So, if it is relatively dry, you may get a very different results as compared to a relatively wet concrete cover. So, if you are comparing test results, you must ensure that the moisture condition of the concrete cover is also similar in range for both the test measurements which we are going to compare. Otherwise, you will get unnecessarily worried about the scatter in the data, which is not really what is happening in the concrete structure. So, corrosion measurements are very good, but you have to interpret and understand the ways which influence the corrosion measurements, otherwise it is very difficult to get meaningful information out of it. Understanding on how to interpret and what are the necessary conditions of the steel concrete system, these are all very important to consider. Now here is an example where it is showing how this particular test can be useful for judging probability of corrosion. You can see here on the photograph on the right side, there is a pipe going here at the bottom, and then there is a vacuum drain container. So these two are actually shown in the contour map on the left side also, so that you can easily compare these two. As you see here, you can see that on the picture on the contour map on the left side, you can see there is a severe, the red region indicates kind of high probability of corrosion, or more negative. If you look at the numbers closely, you can see this is minus 500 towards that pinkish region, and then you have minus 400 here and minus 400 here, and then as you go towards the green, it is more positive, or in other words less probability of corrosion. So, and there is also a blue line which is showing the crack, and this crack is reproduced as a white line, which is not the sealant or anything, it is just to show where the crack was. Okay. So this type of test helps you in telling what is the probability of corrosion. It does not tell you anything about the kinetics of corrosion, it is only thermodynamics of corrosion, and so only probability you will get, not the rate of corrosion. So, okay. So that is something important to remember, you get only probability of corrosion and nothing about the time. What is the rate of corrosion, because if you want to estimate the service life, you need to know the rate of corrosion, that is something different. I will show you that later, but before that, this is another example of potential mapping of large concrete structure. You can see there again it is actually a wheel electrode. You can see that long areas can be so you can see all these vertical wet regions where the potential measurements were taken, and a contour map was developed as you see here. And after the measurement, the concrete was removed and compared with the section loss, and it was, you can see here, compare these two plots on the right side. If you compare these two plots on the right side, you will see that wherever there is a high risk mentioned, these points here, there you have more and more delamination in this region. Here also it is kind of, that region is showing more higher risk of corrosion, and after concrete removal it was proven that yes, this test is actually useful. But one thing is the moisture condition is something very important to, if you maintain an equivalent moisture condition for all the measurement points, then you will be able to get good data and then be able to compare. It is not just you take this tool, handy tool, and then go to the site and then put it on the concrete surface and take reading and say that this is my corrosion potential, this is the corrosion potential measured, and so you may end up in having a lot of scattered data which may not really give you anything useful at the end. So quality control of measurement is very important when you talk about this kind of test. Otherwise, and also another an important thing to tell is this particular standard ASTM C876, the values which I showed you earlier of minus 350, these values minus 350, minus 250, and all these criteria or guidelines were developed based on steel and concrete used in 1970s. Okay, but today we have a lot of other type of steel and different type of concrete and different type of chemicals we are also used. So all these like corrosion inhibitors, all these will or even we have coated rebars, so they may all have influence on on how to judge or interpret the data, because you cannot use the same criteria given in ASTM-C 876 and apply it on all sorts of steel reinforced concrete system, which will give you very negative interpretation. So, as you see on the top right, this is a RILEM recommendation which is telling basically corrosion level can be considered negligible if the corrosion rate is 0.1 microamp per centimeter square, 0.1 to 0.5 it can be considered low, 0.5 to 1 it can be considered moderate, and greater than 1 it can be considered as high. Now, if we consider this 0.1 and above as corrosion like active corrosion from 0.1 and above, and less than 0.1 microamp per centimeter square, we say there is no corrosion happening. So, we did some test in our laboratory and we found that we did test with mild steel with OPC concrete and TMT or QST steel with OPC concrete, and also with corrosion inhibitors and pre-stressing steel with fly ash of different dosage. So, all these different type of fly ash, different type of SCMs, corrosion inhibitors and 2 types of steel, all this were looked at, and then we found that there could be significant misleading information if you blindly follow ASTM-C 876. We cannot blindly follow ASTM-C 876 because C 876 says that if the potential, this is that critical potential, let us say that minus 350 millivolt, and they say if voltage, if the potential is below that, then there is 90% of corrosion. But what we found is it is not really the case with all the steel rebars. So, you have to really have different ranges for different steel concrete systems. That is still not available, we are working on it, but we are working on it. But the thing is, at this moment what we should do is, if you are given a structure, how do we use this technique of potential mapping? We have to build a contour map, and instead of blindly looking at this minus 350 millivolt as a criteria, what you have to do is develop a contour map and then say that the more negative regions are having more probability of corrosion than the more positive regions. That is all what we can do. I think that we should do at this time, instead of blindly looking for this minus 350, it is not a good approach. So, we have to really go for a comparison between various points on the structure which are made of same steel concrete system. And another thing is, if you make periodic very frequently, let us say after every couple of years we are making potential measurements depending on the importance of the structure, then we can say, okay, from the previous data now the potential has changed to this much. So, there is something different happening, maybe at that in the previous, during the previous inspection there was no corrosion and now there is corrosion. So, this is something very important about this potential mapping. We have to be very careful in using these numbers, and this criteria of minus 350 millivolt should not be blindly used. We should rely on comparative measurements and looking at which area is more positive and which area is more negative, and then say that more negative region has higher probability of corrosion. Now, let us get into another very important parameter, which is chloride threshold. So, this slide is familiar to you, we already discussed this slide, and we are talking about this chloride threshold, which is a crucial factor for the initiation of corrosion. Now, one widely used test method is ASTM G109. The test method itself does not say that it can be used for chloride threshold, but people have started using it for determining chloride threshold based on the time of initiation, or whenever the readings showed initiation of corrosion, and this is heavily dependent on the macro cell corrosion between the top rebar and the bottom rebar. So, you can see 3 rebars on the specimen, 1, 2 and 3. So, the 2 and 3 are connected together, and the top rebar is the one which is expected to corrode, and here is the reservoir where you will place the chloride solution, and then chloride solution penetrates into the concrete and reaches the first rebar or this top rebar, and that rebar will start corroding. And the corrosion depends on because the electrical circuit, I am going to show it in the next slide, but the corrosion rate depends on the electrical circuit. I will show here. You can see here this is the circuit 1 which is happening in most of the experiments with the poor relatively older concrete with more porous microstructure. And you can see here this is the anodic bar at the top, this is bar number 1 and this is bar number 2 and bar number 3 as I showed in the previous slide, bar number 3. So, the circuit 1 between the anodic rebar at the top and the cathodic rebars at the bottom is what is usually happening in this kind of testing. So, this bar corrodes and this is the cathode, top is the anode, the bottom is the cathode. So, this I can say this is the anode and this is the cathode. Okay. And so, the resistivity of the concrete between the anode, so resistivity of the concrete in this region plays significant role in completing this electrical circuit. Okay. The circuit 1 which was in the blue color in the other slide which I showed. So, the electrical resistivity. So, if you have a very high quality concrete, what will really happen when I say high quality, highly durable, very dense matrix or compact microstructure, then what will happen is that the corrosion circuit is something different than the blue circuit which I showed, which is across the top and bottom rebar. So, what will happen in such cases, there might be corrosion, but you will not notice that in the type based on the type of measurements you are taking. So, as it is very clear, it was very clear from this more than a year of testing of different type of, you can see on the first two, the blue graphs is of OPC and the red is for fly ash based system, and the black one is a very highly resistive LC3 concrete system. And we did this testing and then found that when the resistivity is very high, there is no visible corrosion at all on the there is the corrosion indicated by the measurements which you are taking is very low. And how do we take the measurement? We take this I core, we measure the current between the top and bottom rebar, and that is very low. Okay. So, but is that okay to conclude that the system is performing well? Maybe not always, because what is happening is in this particular test we usually measure the current in the circuit 1, which is the blue circuit which you see, but actually what is happening is corrosion is happening with both anode and cathode formed on the same top rebar. Okay. So, which is the circuit 2. So, corrosion is happening on the top rebar itself, but it is not about nothing. When you take measurements across the resistor between the top and bottom, you cannot really make any judgment on that. Okay. So, it really again gives you a false reading. And how we proved, when you opened the specimen we could see that it is already corroding, but really not. You can see the close up here, there is already rust on that, but the measurements taken across the resistor was not at all reliable. So, these type of tests are very good for OPC type concrete, but not good for some of the fly ash based concrete with very low water cement ratio or any other the higher resistive concrete system like LC3. So, the more the resistivity of the concrete, less the reliability of this type of ASTM G109 testing. So, another method is, now we found that in the previous thing we found that the corrosion is happening like this circuit 2. So, one rebar is enough to determine or to study the corrosion performance of the concrete system. So, how can we develop a test method or something? So, there are all another techniques which are available which can provide instantaneous corrosion rate, or basically linear polarization resistance test can be done. It's basically what it does is it gives a very small voltage or perturbance to the steel surface which is embedded in the concrete, and then it measures the current associated with it, and then the slope over here is slope when it crosses that zero current axis is measured, and higher the slope it means higher the corrosion, lower the slope it means lower the corrosion rate. So, and then we take multiple corrosion rate measurements and then try to determine the time at which there is an increase in corrosion rate, and then at that time we can open the autopsy the specimen and then determine what is the amount of chloride at that particular moment. So, as you see here, from here to here the chloride concentration keep on increasing. We are exposing the specimen to more and more chlorides, and at one particular time the amount of chloride at this particular time is good enough, or it is equivalent to the chloride threshold, and at that moment there is an increase in the corrosion rate, and that is how chloride threshold can be determined. This is a typical test setup for doing this type of test with one rebar, like you see in the sketch here, a diagram there, one rebar embedded inside, and this is how the specimen looks like. We call it lollipop type specimen, and it is kept in a small beaker. You can see that here, a small beaker and multiple testing. So, this is a typical corrosion cell test setup, and we need a potentiostat to take the measurements, and these are more details on this test for both linear polarization test and also electrochemical impedance spectroscopy, because for systems like coated rebars coated rebars and highly resistive concrete systems, LPR may not be a good choice. In such cases EIS or electrochemical impedance spectroscopy would be a better choice, but whatever be the case, what we are looking at, or the bottom line principle of this test method is that you expose the specimen through wetting and drying, you expose the specimen to chlorides, and continue incrementally the chloride concentration at the steel surface keep on increasing, and correspondingly you measure the corrosion rate at every cycle, and then find at one point there is a significant increase or statistically significant increase in the corrosion rate, and that is the time when the passive state changes to the active state of corrosion. So, we can say at this point corrosion initiated, then at that point you open or break the specimen and see what is that amount of chloride at the steel concrete interface by doing chemical test, and then you can easily determine, and that particular chloride concentration is equal or defined as the chloride threshold. Now, likewise we have determined chloride threshold, and you can see the chloride threshold is not just a function of the steel, it is also a function of the type of the cementitious system used. As you see here, there were 3 systems used, A, B, C. We can very clearly see there is a reduction in the chloride threshold as a function of the type of cementitious system. So, the chloride threshold is not just a function of steel, but it is for each steel concrete system you have to determine chloride threshold, and then we have to combine that chloride threshold result with the chloride diffusion coefficient results, which I discussed in the previous lecture. So, the combined effect or synergistic effect of chloride threshold and diffusion coefficient both are required to assess which material system can be used, which steel concrete material system can be used. For example, to think about our balanced approach which we talked in the very few early lectures. So, both steel and concrete are important, and both the qualities are the quality of both steel and concrete are important. You have to combine the two effect of both these and then determine the service life, and then choose a steel concrete system which will actually give you the desired service life. Now, once the corrosion starts, and then there is something called propagation phase, which we discussed earlier. Here like this, here you can see this red region here, that is the propagation phase. So, there it is very important for us to know how much is the residual service life. Like let us say the corrosion already started, now the next step the engineer wants to know or the owner wants to know is that how long I have before the structure will before the reinforcement will lose, let us say about 10% of cross section area. So, we need to know what is the rate of corrosion. So, how do we determine the rate of corrosion? So, these are some of the technique, one of the technique available to determine the corrosion rate, and most of the available methods are based on this available instruments are based on this guard ring technique, where the area of measurement, as you see on the bottom picture, you can see a circular electrode, and you can see in the person on the bottom right, he is actually putting the similar type of another electrode on the road surface, and then you take the measurement. So, there are contact instruments with direct contact is available, and also the non-contact instruments are available, but again you have to really look at the reliability of these different type of instruments based on some pilot studies. Anyway, the idea is you confine a small region on the reinforced concrete system, that is the region just below this circular electrode, as you see here, the circular electrode, and there are also rectangular type electrode, but the point is the just area below the electrode you have to confine and then take the measurement only in that region. Okay. So, that is this guard ring technology. So, you can see here the horizontal, this is the rebar, and then you have a counter electrode over here you can see, and another counter electrode, center counter electrode, and then you take the measurement. So, this is the circular counter electrode. So, both this and this are same piece. Okay. So, it is the circular counter electrode, and then you have another counter electrode at the center, and then you take the measurement and they be able to determine what is the rate of corrosion. And once you know the rate of corrosion, either by using a linear or assuming a uniform constant corrosion for the wet period, and then for the dry period some other rate, and then you can actually determine how long it will take for the reinforcement to lose x amount of cross section, and then that will help in telling how to budget money for that particular repair work if necessary. Now, we discussed various tests for concrete durability, and then various tests for steel, all that, and then also one thing is how do we ensure that the quality especially when you talk about a repair project or when you talk about a new construction, whatever repair work is being done or whatever new work is being done, the quality of construction or repair, if how do we ensure that it is going to be very high. This is one way, and which was proven to be very successful. This a criteria which was written in the contract document itself. Like you give a contract document, whether it is for new construction or for a repair project, you see some criteria. This is an example with an oxygen permeability index criteria, but you can develop similar criteria based on other tests also. So, here the idea was if the OPI, oxygen permeability index, what the contractor says, the owner told to the contractor that after the construction is over, we will do a performance test at random locations on the constructed facility, and if the oxygen permeability index is greater than 9.7, then the contractor will get 100% payment. If it is between 9.25 and 9.7, then the contractor will get only 85%, that is 15% penalty. If the OPI is between 8.75 and 9.25, then there is 30% penalty, and if it is less than 8.75, then the concrete is or that particular structural element is not acceptable, means no payment. So, when you put conditions like this or attach durability to the money, the payment, then definitely it is like a watchdog. The person at work will definitely know that if I do a good job, I will get quick money, or there will be no delay in the payment or no reduction in the payment. But if the performance of the concrete is not that good, then there will be some impact on the payment. So, if that kind of condition is set, and in this particular project which was done in South Africa, and what they found is almost all the concrete elements were having having an OPI of greater than 9.7. that means no issue, and at the same time the payment same time the concrete structure also was found to be highly durable in nature. So, this is one way of ensuring the durability for either for new construction or for repair. So, all you have to do is you have to define a particular performance indicator and or a performance test, and then put it in the contract that post construction or post repair this particular type of test will be conducted at random locations, and then based on that only payment will be released. So, if that kind of contractual agreement is made, then it is definitely we will see much more durable concrete structures and much more durable repairs also. So, this is a typical how do we look at these different tests and a combination of the test parameters. So, for example, here this is one case, I will just say if the surface resistivity is greater than 20 and the RCPT charge passed in the RCPT test, it's okay, is less than 1000, and then any of these three and this and this is an OR condition, it is also an OR condition. So, what we can do is we can come up with a combined conditions, a combination of different test results, and see which combination, if a particular combination if it is met, then classify the concrete according to that, rather than just looking at one particular test method. So, multiple test methods, and in the recent past we are seeing that more and more structures, people are actually getting more and more serious about doing durability test, not only compressive strength test, but also other tests are becoming more and more popular, and the main reason is that we are seeing more and more failures of our structure much before the design life is achieved, and that is a great big concern for everyone, because as we build more and more structures, we have to ensure that they will also achieve their design life and not face not experience premature corrosion. So, it is very important to adopt durability based testing and come up with performance based specifications in the contract document itself, and if we can connect them to the payment then it will be really great. Yes, it is very difficult, but somewhere we have to start thinking in that way. And also preventive maintenance approach is very important. As you see in this building on the left side, you can see there is a lot of damage and lot of small trees are actually growing. This is an example tree growing on top of a chimney. Okay. So, what is that engineer who was in charge of this building doing? I mean, so who is responsible? So, we need to really have preventive maintenance strategy, So, we do not want this tree growing on top of the chimney for any reason, I think. So, we really have to stop these things from happening, or routine maintenance is very important, and preventive maintenance, what it means is maintain the structure and do things by seeing what will happen in future and do things to prevent those deterioration mechanisms from happening. Okay. So, to summarize, today we discussed about residual cross section, and residual cross section and and stress strain behavior of steel. And then we also looked at how to measure half cell potential and corrosion rate and how they can help in determining the probability of corrosion and also the remaining service life respectively. And then service life, when you estimate, we must look at both chloride threshold and diffusion coefficient. Do not make judgment or selection of materials based on either one of them. You have to really look at both chloride threshold and diffusion coefficient and how the combination influences the service life, and then choose appropriately. And then acceptance and rejection criteria, like connecting money or the payment to the performance indicators, and that will be something very useful to ensure that the structures which we build and the repairs which we do are actually going to be long lasting. And finally, we discussed about preventive maintenance. There is nothing is better than preventive maintenance. So that will really save a lot of money in future, because corrective maintenance is usually much more expensive than preventive maintenance. It is similar to prevention is better than cure, which we all know. And these are the references used for this presentation. Okay, and this will end the module on this condition assessment, and next we will start looking at various repair strategies.